Hi, everybody. Welcome. This is going to be 4 lectures. We have 4 lectures together, 2 hours each, with pizza. So I know that that's why you guys are secretly all here. And all of these lectures will be to give you an introduction to this thing, the black hole information paradox. I'm sure it's something that you have all heard about, but what is it really is the subject of this course. So, so this course is going to be, a kind of hybrid lecture tutorial style. So I want you guys to look at your neighbors and get to know them, because I'm going to give exercises that you guys are going to work together. So take a little moment, say hello to each other. I'm serious about this, just because, yeah, you're going to be splitting up into groups and playing with each other whenever I pose what I think should be a doable problem within the time. Okay? All right. So, and I should just, like, a little bit of parameter searching. How far over here can I write without with it being visible? Is this good? Everything is visible to you guys? Yeah? And here everything's visible with the glare and everything? Yeah? Okay. So, I also am going to give a speedometer. So this is technical on this side and conceptual on this side. And today's lecture is right in the middle. So I'm going to do a little bit of conceptual stuff and also a little bit of technical stuff. Okay. So the whole question of the information paradox comes about in trying to understand the following object, which I'm going to call Z gravity. So Z gravity is a functional of the metric G mu nu and some scalar fields. And it can be written as the following object, something called a quantum path integral. Okay? Quantum path integral means we integrate over metrics G mu nu and field configurations in some space-time. And there is a weight for this integral. There's the Einstein-Hilbert action and the matter action. Okay, so just so that I get an idea, when I write things like this, like a path integral, how many of you guys feel confident you know what that means? And be honest. Be honest. Raise your hand if you feel like you're confident. Raise your hand high so that I can see it. Okay. Yeah, most of you, some didn't raise your hand all the way high. So we're going to try to review things for the people who don't. And we're going to take it slow. The whole purpose of this lecture series is to take everything slow. And it doesn't matter if you know more. You're not special, because knowing more is not time independent. Okay, so but before I get into a review of what path integrals are and what they aren't, I'm just going to tell you that this part is the part that we would say is more understood. This part, everybody agree? That's better? So this part is the thing that we would say is more understood. And this part is what we would say is the less understood part. So we have a rough idea of what it means to integrate over metrics, but we don't really understand it, whereas we have a pretty good idea of what it means to do the path integral over quantum fields. And when we try to incorporate both together, that's where we run into problems. Okay. Now, before we get into some more technical stuff, some big questions. So, isn't it true that the gravity path integral is an effective theory? All right, now raise your hands if you confidently think that you understand what it means for a theory to be effective. Okay, so this question is the following. Let me rephrase this question. So when we do quantum field theory, we're interested in processes that have a particular energy. So in QFT, we want to study processes at an energy below some scale, and I'm going to call that scale MP for now. And that cutoff scale is a parameter which tells us that, you know, at energies above this parameter, we don't really understand what's going on. The physics in my theory becomes strongly coupled. There are interactions which I thought that I could neglect, which I no longer can neglect. And so it's safe to say for an effective theory with a cutoff MP, so long as we restrict ourselves to processes where the energies are much below this cutoff scale, we're safe. Okay? That's the basic idea. And quantum gravity, some people might argue, is no different. We have this cutoff scale. It's often referred to as the Planck scale. It's related to the Newton constant. And so long as we consider energies that are much below this cutoff scale of M Planck, then the gravity path integral should be safe. A safe thing to reliably compute with. And what you should, the takeaway is that the black hole information paradox reveals problems even for energies much below the Planck scale. So it's not a breakdown that we can probe because we're probing somehow high energy physics. You can formulate the problem entirely in the low energy effective field theory framework and still encounter a paradox. Okay, so it's not, the resolution to the paradox is not that somehow we have trusted this outside of the regime of validity that we usually think. Sorry, let me restart that sentence. It's not that we have somehow tried to use the gravity path integral in a regime where we shouldn't have. Really, if we're being very careful, we have done we have used the gravity path integral in places where we should reliably trust it, and still we will find that there is a paradox, that we can formulate a sharp paradox. Is that clear? Okay. Now, the second question. Do you guys know what holographic dualities are? Raise your hand again so that I can see. Okay, not, so it seems like the complement of the people who raised their hands with the path integral, which I find confusing. Okay, so the second question that we want to address before we even begin to do anything is doesn't holography save you? So the statement of holography means that gravity, quantum gravity, is equal in some sense to standard QFT in some different variables. And if we can reformulate gravity as a standard QFT in different variables, then somehow we have gotten rid of the problem. Like I said in the beginning, this quantum field theory path integral is, we think we understand it, and therefore, if gravity is really holographic and we can use the standard rules of quantum field theory, then there shouldn't be an information paradox, right? Yeah. Yeah, so there is a viewpoint that, well, in ADS, the dual is a CFT, but there's a belief that quantum gravity in generic spacetimes is holographic. There's no exact duality known, and there's like very little in ways of models that you can write down that have this behavior, but some people believe it. I'm not subscribing to any viewpoint. It's just that say that this were true, even outside of the realm of ADS, in which case it wouldn't be a CFT, it would be some quantum field theory. Then, yeah, that's the statement of this equality. Any other questions? Okay, so if you have an equality like this, haven't we solved the problem? So that's question 2. And the answer to that question is no. Sadly, as we will see over the next 4 lectures, the black hole information paradox is really formulated in the language where you have a metric that's dynamical. And no matter what your solution is in the standard QFT, you need to reinterpret all those calculations in the original gravity variables. And until you do that, you haven't solved the black hole information paradox. It's not enough to say we're using the rules of standard quantum field theory, and therefore there shouldn't be a problem. You have to explain how the problem is resolved using this equality, not just invoking that this equality saves you. Okay? So until you do that, until you explain how this type of equality would resolve the information paradox, the problem still stands. You need to go back from holographic duality back into the gravity variables, phrase the problem in that way, and then explain why such a duality would save you. And that hasn't been. Okay? So those are the big questions. And we're going to try over the next few lectures to formulate in a sharp way what the information paradox really is. And formulating it in a sharp way is actually one of the hardest things. Because when you have a sharp problem, only then can you have a sharp resolution. If you have an approximate problem that is up to the interpretation of whoever is studying it, then there can never be a sharp resolution. Okay, so hopefully by lecture 4, we'll have introduced a sharp problem, and hopefully by lecture 4, we can start talking about what it means to resolve the problem. Okay? All right, so now we need to go back to the basics. Before I go to the very basics, are there any questions about the outlook for the next 4 lectures? No? Very good. All right. Okay, so right now, I'm going to try to do a lightning review of path analysis. So we're going to do a quick review of path integrals. Hopefully, those of you who feel confident about them will recognize all the stuff that I'm going to say. Those of you who feel less confident about it, this might be a little bit quick. Feel free to stop me at any time, ask questions. It's okay. Okay? Okay. So in general, in a quantum mechanical system, we're interested in transition amplitudes. Okay, so what is a transition amplitude? So say you start at time t equals 0, and you have a quantum state, psi. And you are evolved to t equals capital T, and you have a different quantum state, phi. Then the transition amplitude is the overlap between the state phi and the at time t and the state psi at time 0. So this is what we call the transition amplitude. Can everybody see this with the? Okay. So how do we write this? So there are 2 pictures in quantum mechanics. One is called the Schrodinger picture. One is called the Heisenberg picture. I don't really remember which is which because they're the same thing. But the point is that you can either take the states to be time independent, or you can have them have intrinsic time, and then carry all the time dependence in the operators. So we can write this as the overlap between 2 states at phi equals 0 at time t equals 0, and then a time evolution operator that takes this guy to time t equals t. Okay. So we're interested in objects like this. Okay? And this state psi can be any state of the quantum field, and this state phi can be any other state. So now let's just look at when psi and phi are position eigenstates. So we're just going to compute this amplitude when psi and phi are position eigenstates. Okay? And we're going to do the following thing. So now I'm going to say this is x initial, this is x final, position eigenstates. Thinking about a quantum mechanics with 1 degree of freedom. And now we're going to break up this path integral into a bunch of short time steps. Okay? So, so we're going to break it up into a bunch of short time steps of time epsilon. And so we're going to write this amplitude as a product from I equals 1 to n, I equals 0 and minus 1, of let me write that as k. And I'm going to integrate over all these dqks. Okay. Does anybody know what I just did? Yeah, for every time step, I introduced a resolution of the identity. So it's a statement that 1 is the same as qk, tk. That means that if I insert this object inside of here, I have not done anything. I've just introduced 1. And these tks are just k times epsilon. Okay? Now, let's look at one of these. So yeah, so maybe I can write this a little bit better. So what I mean by this expression is that I have qft integral of dq n minus 1 integral dq n minus 1 qn minus 1 t minus epsilon qn minus 1 t minus epsilon qn minus 2 t minus 2 epsilon, and so on and so forth. And I'm integrating over dqn minus 2 as well. Is this clear that this is what I mean by this equation? I've just introduced at every time step, a complete set of states. I've inserted the complete set of states inside the path integral, and then I have written my path integral as this product of short amplitudes. Okay? So that's what I mean by this line, even though I might have written it in a not so optimal way. Okay, now let's look at one of these. So let's look at Q m plus 1 T m plus 1 Q m T m. So we have to understand what this thing looks like in order to understand this path, right? Everybody agrees? Okay, so how are we going to deal with this? Well, we're going to write it like this. Does everybody see what that is? Well, yeah, we're gonna hold on. Let me. I have my notes on this somewhere else. Yeah. So the reason that we don't do that is just to make sure that we are keeping track of what time step we're looking at. We're going to be generic at this stage. Indeed, all of these states are time independent, but we want to label the position eigenstate that we're talking about at what time step we're. Okay? Okay. So, and sorry, this should be m plus 1. The time is the same, but the position is different. Is that clear? I'm writing at each step an integral over all position eigenbases. And at each step, we have a different label. We're integrating over all of these labels. Is that clear? Okay. So now we want to understand this object. Okay. So let me just rewrite it. We have Qm plus 1 Tm minus I epsilon. So this is an object that appears in our total calculation, and we need to understand what this thing is. So the next thing we do is we again introduce the identity, but this time we introduce a momentum basis. The reason we now introduce a momentum basis is because we know that by the standard rules of quantum mechanics, the overlap between a momentum basis and a position basis is e to the I p q. This is just a plane wave function. Okay, so we're going to use these two facts to study this. we're going to write this as the integral, or dPn, del here. This is what just quantum mechanics of one variable. So these delta function. So yeah, often when you get delta functions, you're thinking about quantum field theory. Okay, so so another thing that we're going to use is that so this is a coefficient h of p and q times the matrix element p, q. All right. So using this fact, we can use the fact that this is a small time step, epsilon, and only up to errors of order epsilon can we pull this this matrix element out and write this integral as and then now we use, so this should have been n plus 1 again, because this is n plus 1. And now we use our wave functions. Okay. So this is plus order epsilon squared in the integral. Okay. So does everybody see where I got this line? I used this fact to pull this guy out, e to the I h p epsilon. And then I used this fact that we have pq is e to the I pq for this guy times this guy and this guy times this guy. These are these guys. I mean, these depend on what the Hamiltonian is. They have, you can work it out. I mean, yeah, so you have to give more specifics about what H looks like in order, how it commutes with the P's and the Q's, so on and so forth. Any other questions? Okay, so I'm going to pull an epsilon out. Of this part. Okay, so now we can go back here and we can clearly see that in the limit that epsilon goes to 0, this will be like epsilon is like dt, and this is like a dq, so this is like a dq dt. Okay, so it takes just a couple of steps to show that this, in the limit as I take my time step to 0, this epsilon step, I erased the drawing, this epsilon step to be smaller and smaller, then I can write this as dp path integral and a dq path integral, where these mean that I integrate over all possible p's and q's. So again, this dq is the limit of the product from k equals 0 to n minus 1 being a continuous function. The time step label becomes continuous. Okay? And same with the p. This is the limit of taking this product to a continuous product over p's and q's. And this pq dot, the result comes from this term right here, tending towards a derivative, and this h is this h, and all of this is times dt. Is that clear? And now, for my last trick, this should look familiar to you from classical mechanics. pq dot minus h, if I solve this for p in terms of q, this will give me my Lagrangian. So the final step is to integrate over p. The integral over p enforces the classical relation between p and q dot, so that I just get an integral dq e to the I integral L dt. Okay? So that is to say that when we're interested in transition amplitudes in quantum mechanics, we're interested in field configurations, and of course, when I do this path integral, I have to specify that q at 0 is qi and q at t is qf. So this path integral, which you can think of by breaking it up into infinitesimal time steps, computes for us this object that I have erased, this object of interest, which was the transition amplitude that I started with. Okay? There's nothing beyond that. This is another way of writing this object. If you can compute this object using the standard rules of quantum mechanics, you'll get an answer. It will depend on your Hamiltonian. And it's related to this object, which we call a path integral, only by going through this series of steps and approximations. But there's nothing mystical about it. It's an object that we use to compute these amplitudes. Okay? Are there any questions about that? So the way that it works is if you assume h is quadratic at most in p, then you'll see it immediately by doing the saddle point approximation for that integral. But otherwise, yeah, you have to work a little bit more. Any other questions? We're usually interested in theories that only are quadratic in p. So it's a safe move to integrate over p and get the Lagrangian here. But as with everything, you have to question, where things come from. And it may be that sometimes when we work with With Lagrangian theories, we actually made a mistake if the Hamiltonian isn't quadratic in P. Any other questions?
When you do simple is that exact with the corrections?
This one? There's always corrections. So in quantum mechanics, this object L, usually we work with the classical Lagrangian, and then the quantum path integral is given by this. But the rules of quantum mechanics are miraculously self-consistent. So if you neglected terms in L, they will show up when you try to compute things via things like loop diagrams and so on and so forth. Essentially, the rules of quantum mechanics tell you that if you work in perturbation theory, the corrections to L will be generated on their own. So. Yeah. Yes. Yes. Any other questions? Okay. Very good. So that's a lightning review of the quantum path integral in one variable, but we're interested in QFT. QFT is the same. It's the same, except now we don't have just P and Q for one variable. We have P and Q for a continuum, right? So the variable of interest is not the wave function of a single particle. It's the wave function of a whole function on a time slice in space-time. So in quantum field theory, we have a field. So this is some slice, let me say t equals 0, and I have some field. It can be, think about if you want, so this section is removed to QFT. So think about, for example, an electromagnetic field. But you can think about any field. So another field would be the wave profile of shallow water waves on the surface of water at the beach. That's another field. It depends on, where, how deep, and where along the coast you look, and then there's going to be some profile. And we call that a field. It's just a function. We call it, let's call it 5x. Okay? And the quantum field theory language for these functions is very similar to the language when you have 1 degree of freedom. You're interested in the transition between one field configuration at t equals 0 and another. So I'm going to call this phi I of x, phi f of x. Now x are these directions. And in QFT, we want to compute phi f of x comma t, phi I of x comma 0. And this is computed, again, by a path integral, just like this one, where we write d phi of x. Phi at 0 is equal to phi I of x. Phi at t is equal to phi f of x. And we weight it by the classical action. It's exactly the same. The only thing now is that the integral is not over a single variable, q. It's over a whole field configuration. Okay? So I'll remind you that you would write this as phi f e to the minus I h t phi I. Okay? So that is a transition amplitude of a quantum field. You should think about it as just a special, a little bit more complicated version of this. We have to, alter our techniques because we have a lot of degrees of freedom, but the rules of quantum mechanics have not changed. Quantum field theory is often taught like it's completely a complete departure from quantum mechanics, and that's just unfortunate. It's exactly the same, just you have more variables. Uh, so yeah, and the only thing special for a gauge field is that you have to understand what the measure of this integration is, because there are field configurations which are redundant due to gauge transformations. So you have to be very careful about what the measure is for the gauge field. But it's still the same for the gauge field. Any other questions? In fact, it's also true for gravity. Gravity, viewed as an effective quantum field theory, the measure is something that you would think that you have a problem with because of the gauge invariance of classical gravity. But the problem with the information paradox is more than that. Okay. Okay. So this is the Lorentzian path integral. It's a lightning review. I know that was a lot in a very short amount of time. But these, just remember, these are the objects that people are computing whenever they write down something like this or something like this. They're just transition amplitudes from one time to the next. You have a field configuration at time 0, you have a field configuration at time t, and you're asking what is the transition amplitude? What's the probability that you're going to go from one configuration to another? And the rules of quantum mechanics just tell you how to compute one or the other. There's nothing mystical about it, right? Okay. Any questions about that? Okay, so now that we've gone over that, I want to tell you another thing that I think is unfortunate, which is that oftentimes it's not taught in this way, although it should, that these transition amplitudes have a very important and deep connection with statistical mechanics. Okay, so let me try to explain that now. So QM to StatMech transition. Okay, so what is the relationship between this and statistical mechanics? Okay, so the relationship between path integrals in quantum mechanics and path integrals and statistical mechanics happens when you start to think about quantum field theory in imaginary time. Okay. What do I mean by imaginary time? So imaginary time is exactly what it sounds like. I take this time of the transition amplitude and I just analytically continue. Okay? So when I do that, I am interested instead in computing phi f e to the minus h tau. So this minus comes from the fact that minus I times minus I is equal to minus 1 times phi I. Okay? So now all I have to do is write this as the same path integral, phi 0, 0 to phi I, phi at tau is equal to phi f, e to the minus s Euclidean. Okay, so the minus s comes from just the fact that this action is a time integral, and then there will be some sign changes, but whatever appears here is what we call the Euclidean action. If you want, the Euclidean action is the result of doing this analytic continuation to the Lorentzian action. It's nothing more than that. Okay? Okay, and it's still computed because I haven't changed anything. It's still computed by the following path integral. Okay? So this is something I want you to just stare at for a second. Let it stew in you for just a moment. And I want to just see how many people are awake right now. So when I am interested in statistical mechanics, what is the first most important object that people compute in statistical mechanics? Partition function. What's a partition function? Say that a bit louder. Okay, very good. Okay, that's good. People are awake, happy. I didn't see anybody get coffee earlier, so so is the worry. So in StatMech, object of interest is this partition function z of beta. Z of beta, we write it as trace e to the minus beta h. Okay, so how can I turn this object into a trace? Okay, so step one, button it up, phi e to the minus h tau phi. Is that enough? I have to integrate over phi. Okay, so this is like setting the eigenvalue together, and this is the trace part. Together they're the trace part, right? You take the trace of a matrix, you have a matrix Mij. Remember, this is a matrix element. I have a matrix Mij, and I'm interested in its trace. It's the sum over I, Mi. So exactly what you do is you button up these guys, and you integrate over all the field configurations. Okay, so how do we write that in this language? So in this language, it's the same path integral. We're integrating over all field configurations, but what we need to do is ensure that we are only considering field configurations with periodic boundary conditions. So what that means is that I only integrate over field configurations where phi of 0 is equal to phi of tau. I still have e to the minus s Euclidean. Okay, so I can draw that diagrammatically as follows. And we are making sure that all field configurations are tau periodic. Okay? So tau, this object that I call tau, really, I might as well call it beta. Let's go back. Phi 0, phi beta. You'll notice that this is the trace of e to the minus beta h. So all we've done is we've related quantum field theory in Lorentzian time through a series of analytic continuations with statistical mechanics. So that's one takeaway. Some of you may have known that already. Some of you may not. But the takeaway is that quantum field theory in imaginary time with periodic boundary conditions computes for you a statistical average. Same kind of statistical average that you compute when you study stat mech. So, you know, again, it's kind of sad the way that like we do things pedagogically. Stat mech, quantum field theory, quantum mechanics, all taught in very different ways, but really they're all cut from the same cloth. They're kind of the same objects of study, but we don't ever say it that way. Okay, so I just want you to keep that in mind, because this web of thinking relating Lorentzian path integrals, stat mech, thermodynamics, all of that stuff is part of how we think of the black hole information paradox, this web of connecting things in these different ways. And it's important to be aware when people talk about, you know, quantum gravity path integral, thermodynamics, black hole thermodynamics, all of that stuff. This is the kind of underlying, you know, set of transitions they have in mind. So you should not, it should not come as a surprise to you that somehow we're going to use this line of thinking to introduce the black hole information paradox, and more importantly, black hole thermodynamics. So we're going to go into black hole thermodynamics now. I just want you to remember that, you know, the relationship to path integrals is through this kind of thinking. So the paradox is phrased in Lorentzian signature only, but it has to do with, you know, temperature, evaporation. So we're going to go very slowly. My goal is to make everything accessible as we develop these ideas. I just want to, I'm just phrasing things in this way in order for the relations to become clear. Of course, you know, in a general system, when you're thinking about thermodynamics and equilibrium, forget about black holes for a second. It's thermodynamic equilibrium. There's very little that you can say about the Lorentzian evolution of the system, except when you think about things adiabatically. And so we know, because we have laboratory experiments, how to think about, you know, path integrals and real-time dynamics and how they link. In systems where, you know, the dynamics might be more complicated, or we can't build them in the lab like a black hole, all I can say is we have to be very careful. That's all. So So it's just to say that we have to be cognizant of these things, and I completely agree with you, which is why it's important to, lay everything bare. There's, as far as, yeah, it's impossible to formulate the problem without going to Lorentzian signature. It's really a question about initial conditions and final conditions and whether or not there is a unitary evolution from one to the other. But we'll get there. We'll get there. Okay. Now, here comes the fun part of this lecture. First fun part. So now, okay. Remember, z of beta is trace e to the minus beta h, right? So in an energy eigenbasis, we usually write that as the sum over e n of e to the minus beta e, which I'm going to rewrite as sum over e to the s of e minus beta e. And here, all I've done is I've introduced this object, which I call the entropy, which is log of the number of states at energy E. And now I want you to get with your neighbor and derive the first law of thermodynamics. So introduce yourselves, start chatting with each other, take a little bit of time, and try to determine what the first law of thermodynamics is. And I did not tell you what the first law of thermodynamics is, so if you don't remember, ask your neighbor. Okay, guys. So let me tell you how to quickly derive the first law of thermodynamics. Okay, so indeed, I didn't tell you, or I didn't remind you. So let's write beta is 1 over T, temperature of the system. So I can write Z of beta as a sum over E to the minus 1 over T, E minus T S. And when T is small, then any time that E minus TS is big, then the contribution will be very, very negligible to this sum, right? Because E minus TS will be a big number suppressed by 1 over T. So we want to minimize the quantity in parentheses. In fact, we can make this precise if instead of doing a sum, we write this as an integral over dE. And then we just do the saddle point approximation, where 1 over T is our large parameter. In the saddle point approximation, we just need to make sure that d by dE of E minus TS is equal to 0. That's the stationary point. This is the statement that this is either a maximum or a minimum. So we want this object to obviously be, do we want it to be a max or a min? Do we want this combination to be a maximum or a minimum? Minimum, very good. So you're still paying attention. Okay, so the minimum is at 1 minus T ds dE is equal to 0, which I can also write as dE is equal to T ds. That's the first law of thermodynamics. That's it. That's all it is. Yeah, the first law of thermodynamics is technically only true at equilibrium, and you should be able to parameterize this sum using the saddle point approximation. So that needs a small parameter out front. 1 over t is actually not a good small parameter because it has dimensions. So really what we need is a large number independent of the things that we can fix. So for example, if there's a coupling constant out here, so it's not that it's only valid in the low temperature regime, but it's valid when there is a fundamental scale in your problem that you can pull out and make a dimensionless number with the temperature. And when that object is small, then this is when this is valid. So this is the first law. Does anybody remember what the second law is? Sorry, that was a question.
But isn't it just that because E is extensive and basically volume is conformal and then it's basically you always. So
That
works.
that's true. If you assume that the number of degrees of freedom scale with the volume, but the more general statement also holds. So long as you can do the saddle point approximation. That's the question. Yeah, absolutely. The approximation definitely breaks down in various different regimes. This is it only works when you can do this. Okay. Does anybody remember what the second law is? That's right. So second law, so that's the first law. Second law is ds. Okay, so now you guys remember, you're experts at quantum field theory, you're experts at thermodynamics now. It's time to bring it all together and study black holes because, what else can you do now that you know everything? So, according to legend, John Wheeler was thinking about the first and second law of thermodynamics, and he was confused. He thought, okay, what happens, say I'm outside of a black hole. Just so happens I happen to be hanging out in the vicinity of a black hole, and I have a nice thermodynamic system in my hands, which you Brits would love. It's a cup of tea. And here he is with his nice thermodynamic system, nice at equilibrium, has a temperature and entropy, satisfies the first law of thermodynamics. And then he wondered, okay, inquisitive as he was, what happens to the total thermodynamics of the universe if I take my cup of tea and throw it into a black hole? Does the second law of thermodynamics hold? Does the process of the first law of thermodynamics apply? So Wheeler posed this question to his PhD student at the time, a guy by the name of Jacob Bekenstein. And Jacob Bekenstein took some time, and he came up with an answer. Okay. So if I draw a Penrose diagram, how familiar are you guys with that object? Raise your hand if you know what a Penrose diagram is. Okay, great, everybody. Perfect. Okay, so I've written down the metric over here for a black hole with charge and angular momentum. But I'm going to draw the Penrose diagram for a Schwarzschild black hole. Okay. The Penrose diagram for a Schwarzschild black hole looks like this. It's an object that has two external regions, maximally extended Schwarzschild Penrose diagram. And then, is it okay if I close this door? This is the maximally extended Schwarzschild black hole.
Sorry, this is an unrelated but important question. Doctor text me the rates of time of who wants pizza. I just think it was okay, 20, 15, 20. I'm not very good at estimating.
20, 22, 22, 20, 20, 25. Say. Grad students eat for 2. Come on. All right. So there was this question: what happens when you throw your cup of coffee into a black hole? The black hole is a black system, completely impossible to extract any information out of. The interior of the black hole is completely causally disconnected from the observers outside. So it's impossible to measure anything from the black hole. So it's impossible to get a good sense of whether or not it's a system that's also at thermal equilibrium, and if so, if it obeys a first law or a second law. So Bekenstein had his homework problem. He spent many months trying to think about it, and he came up with an answer. And the answer was that if the black hole has an entropy, it can't be related to the volume. Okay? So you guys know the answer, that the entropy is related to the area. Very good. So why is it not the volume? Any guesses? No, no, that's not it. There we go. What volume? What volume? When I work in general relativity, I have Cauchy slices that I can draw. And I'm free to pick whatever Cauchy slice I want. So here's one. And here's another. Can anybody tell me the difference between these two? Yeah, so what would happen? What would be the volume in the second Cauchy slice? Say yes, 0. There is a slicing where you could say that the black hole has 0 volume, and in fact, it's time independent. So even if you throw the the cup of coffee or the cup of tea inside the black hole, you could conclude, if you make a particular gauge choice, that the volume doesn't increase at all. So that's the bad answer. Yeah. The volume of the Cauchy slice is not 0, but the part inside of the black hole has 0 volume because it's all null. It follows a null ray. That is the boundary of the black hole. But a complete Cauchy slice is something that it has, well, in 4 dimensions, well, in any dimension, it's codimension 1. So that means that in 4 dimensions, it's 3-dimensional. And so the volume, you can consider subregions of that volume. So it's 3-dimensional surface. It has some subregions that are also volumes. But the volume of a null surface would have 0 volume because you compute it using some set of rays, and if the rays are null, they have no length, and so you can't. So that's why this part of the Cauchy surface is 0. But I mean, the other answer holds too, because you could consider a different Cauchy surface where the volumes get very big, or very small, whatever. So, so the volume.
What about notion of like extremizing or possible farming that has to be a determinant constant which takes finally
Yeah, but then you have to answer who ordered that. And the so a good notion, the reason that Bekenstein landed on it was that this was a very minimal idea, is that, well, you throw a cup of coffee into a black hole, the black hole area increases, and so maybe the correct thing to think of is the area rather than the volume. Okay? Any questions about that? Okay, so the area is defined here. So say you have some, it's codimension 2. So it wouldn't, yeah, you wouldn't have this, would be defined at one time. Can't extend it and shift it. You might have a different Cauchy slice or a different Cauchy slicing, but once you fix the Cauchy slicing, there's a natural evolution of slices, and the area will change with time. Okay, so so these thought experiments led Bekenstein to posit that the entropy, so here I'm going to use S as entropy, not action, is proportional to the area. But the proportionality constant was hard to pin down, and it took a calculation of quantum field theory in curved spacetime to figure out this proportionality constant. Now, we're going to go through that, but not this lecture. I'm going to go through the argument for how you fix the proportionality constant, but not in this lecture. Okay? So the proportionality constant in appropriate units is A over 4 G nu. And that was Hawking. So this is Bekenstein and Wheeler. And this is Hawking. Okay. So so this was the basic idea, that via some calculations, you do some adiabatic processes, you change the mass of a black hole slightly, you'll see that its area increases. And we're going to go through, not that calculation, but we're going to go and see a little bit how that works in this context of this charged and rotating black hole. Okay, so a first step to testing and seeing whether or not this geometry, this black hole geometry, okay, so a few things about this black hole geometry. I'm not going to draw the Penrose diagram for it. You can find it in any textbook on GR. It's a very standard metric, but I want you to observe two things about it. One is that it's not a solution to vacuum Einstein's equation. You need to add electromagnetism. And the electromagnetic field that supports this geometry I've written in a particular gauge. So there is an electrostatic potential part, Q over R, the standard electrostatic potential. And then there is a rotation part. So this is proportional to A. A is proportional to the angular momentum of the black hole divided by its mass. So this J is the angular momentum. And this M is the mass. Okay? So this is a black hole. It has charge Q. It has angular momentum J. Okay? And you can tell what the charge of the black hole is by looking at, well, you can compute it the way that you do in standard electromagnetism. Measure the electromagnetic field at infinity, and you try to see, what the total charge is. It's Poisson's rule. Okay, so now we want to just verify the first law of thermodynamics for this. So we need a ds. So first we need to compute S, right? And if we want to compute S, we need to compute the area. Okay, so first of all, I need to tell you that the horizon of the black hole, where is it located? It's not so obvious where it's located if you look at this metric, but it should not be surprising to you. If it is surprising to you, we can go over it, but it should not be surprising to you that the horizons of this metric are where GRR inverse equals 0. Which is also where delta is. This is a relationship that's also true for the Schwarzschild black hole or for any non-rotating black hole. Okay, so delta equals 0. So delta is this object right here. And I'm going to set G to 1 for the rest of the lecture. So I'm going to work in units where G is 1, just so that I don't have to keep writing it. And the roots, so delta is a quadratic equation, has 2 roots. The roots are very simple to write down. So delta equals 0 at these 2 roots, r plus minus, which are given by m plus or minus the square root of m squared minus q squared minus a squared. So you see, when q and a are 0, you recover the Schwarzschild black hole horizon, r equals 2m. But whenever there is charge, it reduces the Schwarzschild radius. Same with the angular momentum. Okay, and remember, this a is related to j using that relationship. So this is j squared over m squared. All right. So just to test you again, I have this metric now. How do I calculate the area of the horizon? What do I need to do? Who knows? Very good. Do I have to do anything with t? Right, so we set dt 0 because we're interested in a single time slice. And we set dr 0 because we're interested at a particular radius. And then we look at the rest of the metric. So the induced metric at r equals r plus is just rho is this combination here. Rho plus is where I just set r to r plus. Okay. From here, what do I need to do to compute the area of my horizon? What's the next step? Very good. So what's the determinant of the induced metric? Should be straightforward. What is it? Very good. And this should be squared. So I want to compute the integral from 0 to 2 pi d phi, the integral from 0 to pi d theta, then square root of det g. So I have sine theta r plus squared plus a squared. And you should know what the answer of this integral is. Can anybody tell me? Four pi r plus squared. So that's the area. And I'm going to write, so the area is 4 pi r plus squared plus a squared. And you're going to have to trust me that I can write this as 4 pi times 2m r plus minus q squared. Okay, so now in my units, what's the entropy? Divide by what? No, you have the answer. Yeah, very good. So S is just this. All right. So now we're going to show that this obeys the first law. Okay, to do that, we want to compute ds. So ds, I'm going to write it down, is pi times 2r plus dm. So m is going to be the parameter that we use to parameterize the energy of the black hole. Mass and energy are the same, special relativity. So m is going to going to be what we're going to consider as dE. Okay. So I'm going to take derivatives with respect to m, but this black hole also has angular momentum and charge. So I have to make sure that I keep track of q and j. Okay. So we're going to derive the whole first law in an ensemble with angular momentum and charge. Okay. So other than dm, I also have plus 2m dr plus dm. That comes from taking the derivative of r plus with respect to m. Yeah. And then plus dr plus dj plus dr plus dq. That's, now we've taken care of this term. And we have to just take care of this term. So we get minus 2q dq. And this parenthesis closes this parenthesis. Okay, now we just need to collect terms. So ds is equal to pi times 2. If I write here, can everybody see? Yeah. 2r plus 2m dr plus dm dm. You can see that. Minus 2 pi q minus m dr plus dq dq plus 2 pi m dr plus dj dj. Okay. So that's the variation of S. And if I have done things correctly, this object should be what's the first law? I heard it. Yeah, 1 over t. Very good. That should be 1 over t. That one's the obvious one. This object should be the electrostatic potential phi. And this should be the angular velocity. So let me write these down. So this is angular velocity. And this is electrostatic potential. Okay? So, so if you do the calculation correctly, and at home I invite you to compute the derivatives, dr plus dj, dr plus dm, dr plus dq. You'll derive the following. So you'll derive that t is r plus minus r minus divided by 4 pi r plus squared plus a squared. So that's the temperature that we derived from the first law. The phi that we derived is q r plus divided by r plus squared plus a squared. Now, does that look familiar? Does it look like this? Does it look like this at a exactly, or how is it related? It is at r equals r plus, because the rho, yeah, and at theta equals pi. So it would be the electrostatic potential that would be the difference between here and here at theta equals pi. So this reasonable, seems reasonable. And then the omega that you would find sorry. So there has to be a t on this side. So this is actually phi over t, and this is omega over t. Because when you multiply by t, you get t ds. So let me just rewrite that. The first law should be t ds is equal to dm plus minus phi dq minus omega dj. So, and this is okay. So up to these definitions by t. So omega, what is omega? I again invite you to do this when you're at home, but omega you will find is gt phi divided by gt t at the horizon. So this measures how much your metric is rotating. The speed at which it's rotating in terms of the local way you measure time. So dv dt, the angular velocity. So you just start with this this metric, and you run the crank. You assume that there's a first law, and you get something completely reasonable. And I think that that should shock everybody. Like, you know, it's insane that you have a solution to Einstein's equations, and then you just kind of willy-nilly say, well, I'm going to guess that the area of the horizon divided by 4 is an entropy. And then you get stuff that looks super reasonable. So I'm going to try in the last few minutes. I have until like 12:40. I can take till 12:40. You guys you're the boss. Until the pizza arrives. How about you guys? How are you guys feeling? Good? All right. Okay. So in the last few, in the last, you know, the dwindling moments until pizza person arrives, we're going to try to understand, at least based off of what we discussed earlier in the lecture, why this temperature is something not so surprising, okay? And we're not going to do it for this crazy looking black hole. This is too complicated, and I don't have enough time. So we're going to set J and Q to 0, okay? We're going to go back to the good old Schwarzschild black hole, and we're just going to study that guy, okay? So is it okay if I erase all of this stuff over here and all of that stuff? I'm going to just save one equation. And please promise me that when you go home, you're going to verify all of this stuff. Otherwise, I'll get very mad at all of you. I can't assign homework for this class, you know? Huh? Okay. So I'm just going to remind you of T for the Kerr-Newman black hole, but we're not going to stick with that one. We're going to do, but I'm just going to keep that formula up. I'm going to erase everything else. Okay. Okay. Now I'm going to erase it. Okay. So you GR experts in the audience, you should have the Schwarzschild metric memorized by now. So I'm going to write it down. I'm going to assume all of you could rattle this off. Okay, so is this a Lorentzian or a Euclidean metric? Lorentzian. So remember what we said earlier in the class. If I want to relate a Lorentzian path integral to thermodynamics, what do I need to do? Go to imaginary time. Okay, so let's see why such a temperature shouldn't be so surprising. And remember, the horizon for the Schwarzschild black hole is at R plus is equal to 2m. It's very much what you should remember, but also matches what we calculated before when you set q and j to 0. Okay, so now I'm going to take t to minus I tau. It's exactly what we did when we did the transition to thermodynamics. We took Lorentzian time and we made it Euclidean. Okay? And now I'm going to take my coordinate r and I'm going to write it as r is equal to r plus a new quantity rho squared. And rho squared is, it doesn't have the same units as r, right? Because it's squared. So I have to divide by units of length, and the units I'm going to choose are 8m, convenience. So 8m is also the same as 4r plus. Okay? And I'm going to write my metric in Euclidean time to lowest order in rho squared. Okay? So I'm going to expand this guy and this guy to lowest order in rho squared. So I'm going to treat rho as small. So I'm going to do that. So the Euclidean version of this metric for small rho is ds squared is equal to rho squared over 16m squared d tau squared plus d rho squared plus r plus squared d omega squared. And here I've just dropped the higher terms. So this is r plus is a 0 of the metric. That's why the first order is proportional to rho squared. And here I had to do a change of coordinates. So that accounts for this rho squared being here. And the 4r plus was designed to make the coefficient of this guy 1, the lowest order. Okay? Now, what did we say was important about making our Euclidean path integral related to thermodynamics? How do we make sure that we have a trace? Yeah, the periodicity, right? Okay, so tau, if we're going to relate it to thermodynamics, tau should be periodic, right? I'm going to relate to thermodynamics, tau should be a periodic variable. Let's look at this. We have d rho squared plus rho squared d tau squared. Tau is a periodic variable. This looks like the metric for polar coordinates, right? Let me define a new periodic variable tau over, so 16m squared. Remember, r plus is 2m. So this is the same as 4r plus squared. Agree with that? Okay, and I'm going to define a new periodic variable, tau over 2r plus is equal to theta. So in these coordinates, that's exactly the metric of polar coordinates. D rho squared plus rho squared d theta squared. Okay, so how can I get the periodicity of tau that's naturally induced? Can anybody tell me? All right, how about this? In polar coordinates, what is the periodicity of theta? 2 pi. Polar coordinates. It's not the polar angle of a spherical. That is 2 pi. There's a reason why it's 2 pi. If it were less than 2 pi, you wouldn't cover the plane. And if it were more than 2 pi, you would overcover it. And when you don't cover the whole plane, then you have what is called a conic section, which means that you cut out an amount in the plane, and then there's a conical singularity. Okay? So the fact that it's 2 pi is very important for having a smooth metric. Okay? If you don't, then there's a point where there's a conical singularity. Okay, so theta has to be identified at theta plus 2 pi. And you don't get to choose that. So there is no singularity in polar coordinates. We don't want that, right? In the Euclidean, this is a Euclidean metric. We'll get back to the interpretations of things. But theta goes to theta plus 2 pi is there so that there's no conical singularity in the metric. The metric is completely smooth. The horizon is a place where the metric is also completely smooth, by the way, in the Lorentzian. This R plus is the horizon, not the singularity of the black hole. Okay. So what does that mean? So if theta is identified by theta plus 2 pi, that means that tau is identified as well. So theta plus 2 pi is equal to tau plus beta over 4 R plus, right? Because tau also has to be periodic. So can anybody tell me what beta is? This means that they're identified. You should be able to figure out what, so I take theta goes to theta plus 2 pi, I get this, should get the same thing, which is like taking tau goes to tau plus beta. Maybe another way of saying it is that I should be able to delete these guys and figure out what beta is. Oh, sorry, 2, yeah. That 2 is this one, 2, not 4. So can anybody tell me what beta is? 4 pi R plus. All right. So that means that T is 1 over 4 pi R plus. Let's look at this guy. Okay, so you should be doubly shocked, I think. First of all, we took a Lorentzian solution, we computed a first law, and we saw that if we just assume that the entropy is area over 4, then and m is the energy, then the proportionality for the first law, the T, would be something like this. And that's something that you get assuming equilibrium. This equilibrium rule. Here, I've done something completely different. I've taken a Lorentzian metric, and I've used the rules of relating quantum path integrals to statistical mechanics. So I've taken my time to be periodic. I've ensured everything is periodic. And actually, I get a condition on the periodicity. I don't get to choose the temperature like I did when I did the statistical thermodynamics. Remember, in the derivation for statistical thermodynamics, I got to set this periodicity, this temperature. In thermodynamics, you get to set the temperature. Here, I just demanded that my variable was periodic, and I found that for any periodicity, I would get a conical deficit unless I set my periodicity to be something very particular. So smoothness of the geometry dictated the periodicity of this variable, right? And I think maybe at this point it's a little bit mysterious why the smoothness of the geometry gives the same temperature as the first law. And we'll discuss that more next time.